Routing Room, and today we're going to level up our knowledge on IPv4 addresses. So let's go over some basics first. What is an IPv4 address? It's also known as a Layer 3 address or logical address. And when we're talking about Layer 3, we're talking about Layer 3 of the OSI model, which is that network layer. And we call them logical addresses because they can change, and they can change kind of quickly given different types of scenarios. So if you're on network A, you'll get an IP address associated with network A. But if you roam over to network B, either maybe you plug into a different switch, different outlet, or you are on Wi-Fi and you roam over to a different access point, that may be on a different network and you'll get an IP address aligned with that network. Now each address is 32 bits long, no more, no less, and that's written as 4 octets. So if we have the address 192.168.0.4, each of those numbers is its own octet. So 192, that is an octet. 168, that's another octet. 0, that's another octet. And 4, it's our last octet. Each octet is 8 bits long, and they can range from 0 to 255. So that means any one of those octets that we just mentioned can be from 0 all the way up to 255. Which encompasses binary values of all zeros all the way to all ones, and that's 8 binary values, 8 bits. We use them to identify devices on a network from a layer 3 perspective, and they're used for routing traffic between networks. So if you're talking about routing between networks, we're talking about IP addresses. Your MAC address is used to an extent, but primarily we're talking about IP addresses when we're talking about routing in general. So now let's do some conversions. So we're going to take an IP address and convert it to binary. We'll do the opposite, and we'll do the same thing with hexadecimal, which if you're unfamiliar with hexadecimal, it's a base 16 number system, and it's what you'll see kind of by default in Wireshark. So kind of important to, at least in my opinion, to understand both binary and hexadecimal and how to convert back and forth between the two. So let's start with binary first. So let's take an IP address like the one I just said, 192.168.0.4, and you're like, hey, why are you spreading these out so much? Don't worry, we'll get there. So now how do we convert this to a binary value? So first we're going to take our first octet there, that 192. And what number can we subtract from 192? Well, we can take 128 from 192. We got to start with the biggest number that we can take. Since we use 128, we're going to put a 1 there. And that leaves us with 64. Well, we can take 64 from 64, and that leaves us with 0. So we put zeros the rest of the way because we are done. That's it for 192. So the binary value for 192 is 1, 1, and then 6 zeros. That's our binary value for 192. Go to our eraser over here, get rid of that. Go back to the pin. We'll do the same thing with 168. So we have 168. Now what's the biggest number we can take from 168? Again, 128. Leaves us with 40. We use our 128. Now can we take 64 from 40? Nope, not in this scenario. Not in this case. Not with IP addresses. Can we take 32 from 40? Yes, we can. Leaves us with 8. So we can't take 16 from 8. We can take 8 from 8, and that leaves us with zeros. Get rid of this again. So now our binary value of 168 is 1, 0, 1, 0, 1, 0, 0, 0. Now I'm sure you can guess what the 0 is going to be, right? All zeros. I don't know why these are showing up as polygons now, but sure. So our 0 is going to be all zeros. And then our 4, we only have one thing we take from 4, and that's 4, right? So we're going to do 0, 0, 0, 0, 0, 1, 0, 0. So we have 5 zeros, a 1, and then 2 more zeros. So now that is our binary value for the IP address that we have. So now let's go the other way. And we'll just do one number here for brevity's sake. So let's say we have a binary value of 1, 0, 1, 1, 0, 0, 0, 0. Again, I don't know why there's polygons, but we'll work with it. So how do we do this way? Well, whatever has a 1 underneath it, we're just going to add together. So let's take 128 plus 32. That is 160. We'll take 160 plus 16, 166. So whatever octet this is would be 166 in decimal. And that is how you convert back and forth from binary. Now let's talk about something a little more complicated with hexadecimal. So hexadecimal is a base 16 number system. And if you remember back to kindergarten, we have our ones place, our tens place, our 100s place, our 1000s place, yada, 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 right? Because we work in a base 10 number system. So what this means if we break it down is this really looks like 10 to the 0 power, 10 to the first power, 10 to the second power, 10 squared, 10 third power, or 10 cubed. So we'll take the same thing, same concept, and we'll apply it to 16s instead of 10s. So 16 to the 0 power. Sorry, it keeps zooming in, having some, I don't know why it keeps doing that, but we'll work with it. 16 to the 0 power, like anything to the 0 power, is 1. 16 to the first power, like anything, is itself. 16 squared is 256. And we'll stop there because we just don't really need to go any higher. So let's take a number, let's say 80. And just like with the binary, can we take 256 from 80? No. So we'll put a 0 there. Now can we take 16 from 80? Yes. Well, how many times can we take 16 from 80? So can we take it one time? Yep. Can we take it twice? Yep, that's 32. Can we take it again? Yep, that's 48. Can we take it again? Yep, that's 56. Nope, that's 64. My bad. Can we take it again? Yep, that's 80. So we can take 16 from 80 5 times. That is 80 itself. That leaves us with 0. So our binary value for 80 is this. And 0x, all that does is tell you that it's a hexadecimal value. And this first 0, not always necessary, but in this case we'll leave it in. So our binary value for 80 is a hexadecimal value of 50. So let's do that again with something else. Maybe my brain math will be a little bit better this time. Let's take a value of 300. So in this case, we can take 256 from 300. We can take it away one time. So we'll say 300 minus 256. And that is 44. All right, And how many times will 16 go into 44? It'll be 2 times. Okay, 16 times 2 is 32. One more would be 48. That's too much, so we take that away 2 times. 32 minus 44 is 12. Well, now what do? We can't put 12 in a single spot, right? So what hexadecimal does is once we get to the number 10, we replace those double-digit values with letters. So we have, in hexadecimal areas, we have possible values of 0 through F, where 0 through 9 are your regular 0 through 9s. And then we have A, B, C, D, E, and F, where A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. Now wait a minute. It's hexadecimal. We're talking about 16 numbers, but we only go up to 15. Well, if you count the 0, because in IT we always count the 0 because 0 is a number, we have 16 possible different number values here. So if we see 12, that aligns with C. So this hexadecimal value is 12C. All right, let's do one more, and we'll go the opposite way on this one. So let's say that we have a hexadecimal value of, let's say, A7. So here's how we do this. A means 10. So what we're going to do is we'll say 16, because it's in our ones place, right? 16 times 10, that's 160. And then we're going to add 7 to that, because it's 7 in our ones place. So we have 7 ones, i.e. we're going to add 7 to the value. So hexadecimal value of A7 is equal to a binary value of 167. Clear as mud? Clear as mud. All right, so now we're going to move on to our next slide here. And we're going to talk about different types of IPv4 addressing schemes. So Classful IPv4 addressing was an early method of doing IPv4 addressing. And it divided networks into fixed classes, which means the subnet masks aren't flexible. We'll talk more about subnet masks in a later slide as well. But when we say not flexible, it means that if your first octet was in any one of these ranges, you were stuck with that default subnet mask. You could not vary. There was no variation in what kind of mask you could have. So we have Class A, Class B, and Class C for our users, or what we could assign things to. Class D is for multicast. And with multicast, generally it's an IP address that gets broadcasted, or things join it for specific purposes. And we'll get into that more in a later video. And then Class E, that's reserved for the IANA folks. That's the Internet Association. Sorry, I messed that up. It's reserved for the IANA folks. So the modern day of IPv4 addressing is called classless addressing. And it uses a concept called classless interdomain routing, or CIDR, which means we can vary our network size by our prefix length. And we'll get to that in just a second. It gives us flexibility with our subnet masks, which means that they're not determined by a specific class. So we can have a Class A subnet or a Class A IP address, but we can give it a subnet mask of a Class C address, which means we have flexibility with our subnet masks. Essentially, we're not stuck just giving a class A /8 and a class B a /16, and so on and so forth. So now what is a subnet mask? Well, it defines a split between the network portion and the host portion of an IPv4 address. This goes back to that CIDR notation, which helps us identify how many bits belong to the network. So if we have a /24, that means 24 bits belong to the network, which equals this subnet mask. So if we break this down, if we remember back to the chart we had, the 128, 64, 32, 16, 8421. So a /24, we have 24 bits belonging to the subnet mask, which looks like this. So if we have 255, 255, 255, and 0, from a binary perspective, it looks like this. "24 ones, 24 binary ones, which means all of this belongs to the network. So now we'll talk about private IPv4 addressing. Also known as RFC 1918, that is the standard that defines private IPv4 addressing. Used inside private networks, like your home, or maybe like your office building. Inside your local area network is more than likely going to be private or RFC 1918 addresses. These are not routable on the public internet. And what that means is that for a private address at home for you, if you check your IP address right now, it probably falls in one of those ranges that you see below. Those are your RFC 1918 addresses. For you as a user to have access to the internet, you have to use something called NAT, or Network Address Translation. And what that means is you inside your network, this is your house, give it some windows, give it a door. So for you to have access to the internet, everything inside your house is RFC 1918. Which means everything inside your house can talk to everything else inside your house with these private addresses. But the internet is not inside your house. So you have to be able to get out. So you have your little modem box, right, through whoever your provider is. So everything on the inside of that is RFC 1918. And then the connection out through that coax cable or that fiber cable, this side is a public IP address. So something outside of these ranges down here. And then what happens inside this modem router, whatever, is something called network address translation. So basically what it does is it says, hey, whatever this private address is on the inside, we're going to translate it to this public address on the outside, so that way it can have access to things on the public internet. And through some other magical stuff dealing with network address translation, that packet, when it goes out, knows how to get back to you to give you the website that you're trying to reach, whether it be YouTube, Google, whatever you're trying to use, through the magic of the internet and through NAT, which we'll talk about in a later video. It gets back to you, the user, to give you the web page that you are looking for, or that you're trying to reach, or that file you're trying to download, or the music you're trying to stream, the video you're trying to stream. All that happens through the magic of NAT. So that is all for this episode of the Routing Room, and I will see you all next time.